All right, guys, for question 3, it's a bit tricky, but I think if you put enough time, probably you still can make it. All right, for part 1, question 3, part 1, part A1. First, you need to find all the node voltages, which refer to V1, V2, and V3 here. If you can find these voltages here, that means you can get the answer, including this Vx here. Okay, so Vx is between V2 and V3. So you can say that V2 minus V3 is equal to Vx, right? Okay, there's all the node voltages here. Actually, the node voltages refer to V1, V2, and V3 only. Okay, I can give you the hints here. These 3 voltages, they are really good number here. They are really nice number. That means they are either 40 volt or 20 volt or 50 volt. It's all end with 0. See, it's either 60, 40, or 70 or 90. Okay, very good, very easy to refer number here. Okay, so for the first step you need to use is, first step you sum all the current here using the KCL at V2 and not V2 using the KCL. So we assume, since the IY is flowing in this direction, so we assume the IY is going into the node V2. So for this current, we have no idea whether it's going in or going out. So if we assume it's going out, okay, if we assume going out, this current is referred to as current at 2 ohm here. If the current is going out, we assume here initial assumption. So if you get a negative number, that means the current is actually going the other way. So it's okay to do the initial assumption like going this way. And for this 4 ohm also, we also assume that current is going down. Since here is ground, so the most likely the current is going down. Okay. So this is the initial assumption minus IY equal to 1 in, 2 out. So 1 in minus plus 2 out positive equal to 0. Okay. So after you solving this one, and then you need another equation using the KCL at node 1. So we have one current coming in here. So the current here is a 2Vx. The amplitude of the current is 2Vx here. It's going into this node. Okay, the arrow already showing that it's going to this node, and then this IY is going here. I small I here is going down. So what we can see is 1 in, 2 out. Okay, so you write this equation here, and so 1 in equal to this 2 out. So 2Vx equal to I plus IY. Okay, I give you the hints here. 2Vx here in equal to I plus IY. So this is a small I. So after you use these 2 equations here, you solve for I. After you know the I, this is the voltage source. This is the part 2. Part 2 is find the power of this voltage source. Okay, so the voltage source is a 4IY. So at this time, I think you already know where is how much is IY here. After you solve these 2 equations, you know the value of IY. So you just take 4IY is equal to this voltage. Multiplied by this current, you get the power. Okay, so the power is really good number also. What something watt is 1,000 watt, above 1,000. Something 1,000 watt. Okay. Right. So if you get the wattage of about a few hundred, that means most likely your answer is incorrect. The answer should be above 1,000. Okay, this is for question part 1. For part 2 here, this is very unusual. This question is a bit tricky also. Even though it looks really simple, right? You can rotate this one 90 degree, putting the ground at the bottom here, rotate 90 degree. So what you need to do at this question, for this question is, you need to find the Thevenin equivalent circuit. So for Thevenin equivalent circuit, we have only 2 components here. one is the Thevenin voltage, one is the Thevenin resistance. Okay, we need to find these two, Thevenin voltage and Thevenin resistance. So first, Thevenin voltage is between A and B here. So this is VTH, Thevenin voltage between A and B. We put a positive here, and then we create one. We assume that this node is V1. So immediately you know how much is V1 because this is voltage source, right? Immediately you know how much is V1, and then this is V2. Okay, and then we also have V2. So V2 is equal to Vx. Since this Vx is across 60 ohm, so the V2 is equal to Vx, right? V2 is what we assume. We assume this node is called V2, and then this voltage here, the voltage along this branch, the voltage for this whole branch here is a Vx. So V2 is equal to Vx, right? So you solve for V2, and then you arrive at something volt, really small, less than 10 volt. Okay, less than 10, really small. Again, and then you try to use some analysis here, try to solve for VTH. Okay. All right. And for the RTH here, RTH you need to use the KCL at this node here, V2. Okay. You need to use the KCL, sum of all the current at this node V2 here. Since this node is equal to this node here, since there are only one wire, okay, this wire. So if we assume this is I out here, okay, because in the Thevenin circuit here, in Thevenin circuit we have this VTH, and then we have this Thevenin resistance, and then here is the output terminal to connect to our output load, right? And then this one, let's say we have one current called the I out here. So if you know the I out, you know this one, of course you can find the RTH. This is the purpose of using the I out here. If we know the output current and we know the voltage, of course we can calculate this because inside this loop only 3 components. I out. Okay, we do need to know this IRL is not given, it's not relevant here. But we assume there's one I out here. If we can calculate the I out, that means we can calculate the RTH by dividing the VTH by I out. We get the RTH using the Ohm's law here. Using Ohm's law, if we know the I out, we know the VTH from the previous, for the first part here, then we calculate the RTH for V2. So the KCL at V2 here, you see, we got one current, we assume the I out is going down, okay, and then another, we assume here's I1 is going this way. That means the I1 is leaving the node V2, is leaving. I out is entering the node V2, and now we have to assume another voltage here. I2 is also leaving. So one in, two out. Okay, and then you try to solve for all the I. If you can find the I out, and then you use the previous VTH here, you plug in VTH here, you plug in the I out, you can calculate the last answer for the RTH. Okay, you have to try this one. It's a bit tricky. Okay, it's a bit tricky. All right, that's all for Q3.